This problem appears at the 2019 physics questionnaire of the qualifying examinations for applicants for Japanese government or MEXT scholarships for undergraduate students. The answer key and original questions are linked in the description. Problem 1-1. A car at rest starts moving along a straight line and stops at a time t equals 80 seconds. The velocity v of the car changes as a function of time t, as shown in figure 1-1. Find the distance that the car travels.
Let us recall that the distance traveled by a body is the integral of the velocity curve. So that is the integral of the velocity or the speed with time, which means that it is the area under the VT curve. In our problem, this is the velocity curve or the speed curve. And thus, the area under this curve is the distance that we're looking for. So we find the area of the first triangle, that is 1/2 base times height. Then we have the square, the area of that is just length times width. And we have another triangle. Again, the area is 1/2 base times height. We add them up together and we get this value.
Problem 1-2. A small ball at rest falls down from a height of h above the ground and bounces repeatedly. The coefficient of restitution between the ball and the ground is denoted as E, and the acceleration of gravity as g. Find the maximum height of the ball between the nth and the n plus first impact with the ground.
Let us remember that the coefficient of restitution is the ratio of the relative speed after the collision to that of the speed right before the collision. When we say relative speed, that's how fast the bodies are moving away or towards each other. In this case, the floor is not moving and we have a ball having impact on the floor, and the floor is not moving, it's stationary. And therefore, the relative speed of the ball to that of the floor and vice versa is just the speed of the ball. So the relative speed after the impact is the speed of the ball after it bounces off the floor. And the relative speed before the impact is just the speed of the ball as it hits the floor right before the impact happens. And then we also apply here the conservation of energy. This states that at any point in the impact, before and after the impact, and even after it bounces up to the maximum height, the sum of the energies is conserved. So the kinetic energy plus the potential energy at any point is equal to the kinetic energy plus the potential energy at any point, provided that we are not losing energy in any other mechanism. In this problem, we start with the height h for the ball, and then it falls to the floor or the ground. And when it falls to the ground, just before it hits the ground, its speed is v. This is the first impact, n equals 1. And then it bounces off. However, the collision is not elastic, meaning it loses energy to the floor every time it bounces off the floor. And so the maximum height also reduces. That's because the energy is transferred, some energy is transferred to the floor. And so we have less energy to bounce. And at every impact, for example, at n equals 3, here, the maximum height will again be reduced. And we also notice that the speed also reduces at every impact. Again, that's an effect of the inelastic collision, that some of the energy is lost to the floor. And the problem states that the coefficient of restitution is E. So if we start with a V speed right before the collision, after the collision, that speed will be reduced to V times E. And so after the next collision, the speed will also be reduced to the previous speed times E. And you see the pattern. We are interested in the height after the nth collision, the maximum height after the nth collision. So for example here, the maximum height after the first collision is this height here. After the second collision, it would be this height. So we're going to have to find that. And the way we do that is we compare the sum of energies right at the collision, right after the collision rather, and the sum of the energies at the maximum height right after that collision. So right after the nth impact with the floor, this is the kinetic energy of the ball. So right after it bounces off the floor after the nth impact. And the potential energy is 0 because we're on the floor. And then this is the kinetic energy right at the maximum height after the nth impact. And this is the potential energy at that maximum height. So we see that we can cancel these terms here and the m's as well, and we can just move the g down here, and this is what we get. We see that the height, the maximum height after the nth impact is this expression here. Now we just need to find v sub n, which is the speed of the ball right after the nth impact. And so that takeoff speed after the nth impact is calculable using this expression here, because we know that on the nth impact, right after the nth impact, we multiply it with how many e's? We multiply it with n e's. And so we have e to the n here, and that's from the pattern here. And then we just substitute this bit here into here, and this is what we get. And now we just need to substitute something for this expression here. This is actually a correct answer, but it's not in the choices, so we need to reduce it further. Now, to find this, we have to use the kinetic energy of the ball in here and apply a conservation of momentum, or rather a conservation of energy at this point and at this point, the very first time the ball falls. And so the conservation of energy for this first impact is just the potential energy here, plus the kinetic energy here is 0, so the potential energy is just this. And when it falls down here just before the impact, the potential energy is 0, but the kinetic energy is this. So again, this is just the conservation of energy. Now we can cancel some terms and we can actually get v squared, because that's what we're looking for in here. And we notice that the m's cancel and we get v squared equals this expression. Now we just plug this into here, and we notice that the denominator here very conveniently cancels with this bit, and so we get this expression.
Problem 1-3. Two long straight wires with the same current I flowing in the opposite direction are placed parallel to each other with a distance of 2d as shown in figure 1-2. Find the magnitude of magnetic field H at point P.
For this problem, let's remember that the magnetic field produced by a current carrying wire can be expressed like this. Here we have the wire, so the wire are the dots. So here we have this dot here is a wire. Here we have a dot here, but a hollow dot, and I put an X there to mean that the current is actually moving into the page, into the screen. In this case, the current is moving out of the screen towards us. So here we are looking at the cross section of a wire. And so the wire extends from the front of the screen to the back of the screen, and it passes through the screen. And so we just see this dot here. And so the direction of these two wires, or rather currents, are opposite. This current here, again, is coming towards us. This one is going away from us. And now if you have those currents, we represent them with I. So if we focus on this current here, the magnetic field produced by this current is just this amount of magnetic field. And the I here is the amount of current. The R here is the distance from the wire, which we consider to be a point, so it's here, to wherever we're looking at the magnetic field. For example, if we're looking at the magnetic field here, then the R would be computed from here to here. If we're looking at the magnetic field here, then the R would be computed from here to here. Now, if we're looking at the magnetic field in here that is produced by the other current source, then we have to compute R from here to here. So again, R is just the distance from the wire to the point we are looking at the magnetic field of. And we see some arrows here. These arrows indicate the direction of the magnetic field. So for example, the magnetic field due to this wire here is just to this direction here. If we're looking at it in here, the direction is towards there. If we're looking at it in here, the direction is towards there. So the direction is given by the right-hand rule, and we see that the direction of the magnetic field produced by this current flowing to us is actually counterclockwise. So wherever you are on the circle, you draw a tangent, and that's the direction of the magnetic field. And of course, the direction of the magnetic field produced by this current is actually opposite that. So it's clockwise. And so when we are in this bit here, the magnetic field due to this would be going this direction, and the magnetic field due to this is going this direction. And we recall that the total field at any point is just the vector sum of all the fields at that point. So if we're looking for the magnetic field at this point here, we just need to sum the magnetic field due to this, which is this bit, and the magnetic field due to this, which is this bit. And for example, in this problem, the X components cancel very conveniently because the magnetic fields produced are symmetric with respect to this point. They are symmetric horizontally. Now let us draw the problem. This is the current carrying wire that is carrying current towards us, and this one is the wire carrying current away from us and into the screen. And just like in the previous slide, we can draw the magnetic field due to this, and that would be this red arrow. And this red arrow is a vector, and it has this component on the X and this component on, or rather this component on the Y and this component on the X. Likewise, the magnetic field due to this is this green arrow. Again, it has a vertical component going upwards and another horizontal component going sideways. And we notice that because of the symmetry of the problem, that means the distances are the same, the I's are the same, the only difference is the direction of the current and of course the direction of the magnetic field. And in fact, the only difference is their horizontal components. They go opposite ways, and so we can cancel the horizontal components. But the vertical components actually go the same way, and so we can actually add up the vertical components. And therefore, the total field at this point is just the sum of the vertical component due to this field and the vertical component due to this field. So we call that HL sub Y, which is H left here. This is the wire on the left, wire on the right, and so the vertical component is just Y, and this is the vertical component from here. And because we know that they are equal, we can actually just use either one of them and multiply it by 2. Here we will use the left current carrying wire. So we will use H sub L sub Y, and that is the vertical component of the magnetic field due to the current on the left. And that is just this quantity, which is we obtained from the previous slide, this quantity, but because we are only looking at the vertical component, we need to multiply it by the sine of the angle, and that sine of the angle is simply
the distance, the vertical distance over the hypotenuse, and the vertical distance is r, or rather d, and the hypotenuse is r. So we do the multiplication, we obtain this. Now we just need to express r in terms of d, and we use the Pythagorean theorem because we know from the Pythagorean theorem that the square of the hypotenuse, that is r squared, is equal to the sum of the squares of the sides. So that's d squared plus d squared, and we obtain this. And now we can just replace the value of this one with this one. And then what we're looking for eventually is this h, which is twice this vertical component of the current or the magnetic field due to this current here. So that is twice this value. So h equals 2 times this quantity, which is this quantity. So we just copied it here, and we replaced the r squared in there with this one and here. And some terms cancel, the 2's cancel, the d's cancel. We are left with this expression, which is in the choices. Problem 1-4. A sinusoidal wave travels in the positive x direction with a constant speed of 2 meters per second. Figure 1-3 shows a snapshot of the wave at t equals 0 seconds as a function of x. Find the formula of the displacement y at time t. For this problem, we need to recall how to describe a sinusoid using the sine function. In general, this is the form of the sinusoid. We have a here, which is the amplitude. That is the maximum, or rather that is 1/2 the swing from the minimum to the maximum. In other words, if the average of our sinusoid is at 0, that is just the maximum height of our sinusoid. And then we have 2 pi x over lambda. Lambda is the wavelength of your wave. That means it is the distance before the wave repeats the cycle. And t here, the capital T here is just the period of your wave. That means it is the time it takes for the cycle to repeat. So this is the general form. And we also recall that we have other quantities called frequency, which is the reciprocal of your period. So if you know the period, you can compute the frequency. If you know the frequency, you can compute the period. And we also have speed. And this is important because the frequency and the wavelength are related to each other using this equation here. And so if we know the speed and we know either the frequency or the wavelength, we can compute the other quantity. And because the frequency and the period are related in this manner, we can actually also put a period relationship between the speed and the wavelength. And in fact, if we do that here, so this is 1 over f, and if we take 1 over f, so we put this down here in the denominator, and the v goes down here, so we get this relationship. The period is just the ratio of the wavelength to the speed of the wave. From the problem, we can actually obtain the amplitude, the wavelength, and the period. For the amplitude, we see that our wave actually centers at 0, and it swings up to 3 and back to -3. And therefore, the amplitude there is just the maximum height because the center is 0. So that's 3. And then let's look at the wavelength. The wavelength is just the distance it travels before it repeats. And in this case, that is the distance from here to here, because at this point it repeats the pattern. And that is just 0 to 4, so that's 4 meters. And the period, we found that the relationship between the period and the speed and the wavelength is this expression here. And we know the wavelength, that's 4. And the speed is given in the problem, that's 2. And therefore, the period is this. Now we just replace the values of this, and this is what we get. Now we just have to simplify this a little bit more. We factor out 1/4, move this out in here, so we get a pi over 2 in here,
And this one, because it's 2 originally, we just get a 2 as a coefficient. And this conveniently matches with one of the choices.
Problem 1-5. A movable piston is fitted in a tube as shown in figure 1-4. A speaker near the open end of the tube emits sound waves with a frequency of 555 Hz. When the piston moves from the left end to the right, the first and second resonances are produced at distances 14 centimeters and 44 centimeters from the open end respectively. Find the speed of the sound waves.
The problem mentions resonance, and the idea of resonance is that it is actually the same as when the standing wave or a standing wave is formed in the tube. So that's the resonance inside that tube. And we recall that when both ends of the tube are open or closed, the resonance happens, or the standing wave is formed when the length of the tube is actually an integer multiple, an integral multiple of half of the wavelength of the wave. So if you have a wave and you know half of its wavelength, you can actually compute at which lengths of the tube you can get it to resonate. And we will not try to derive this here, but we just remember this fact. And also, if one end is open and the other is closed, instead of thinking about 1/2 of the wavelength, actually the resonance happens at 1/4 of the wavelength. And if you actually have twice 2 of those 1/4, what you get is 1/2 of the wavelength. And again, that's not going to resonate if it's 1/2 of the wavelength. So we only need the odd numbers. We cannot have 2 1/4 of a wavelength. We cannot have 4 1/4 of a wavelength, because again, they will reduce to 1/2 of a wavelength times an integer. So what we need is 1/4 of a wavelength times an odd number. That's why we have 2n plus 1 here. This is to indicate that we need an odd number to multiply with wavelength over 4. And again, this is for the case when one end is open and the other end is closed. We also recall the wavelength frequency relationship. Again, that's just the speed is equal, the speed of the wave is equal to the frequency of the wave times the wavelength of the wave. In this problem, we are given the frequency of the wave, that is 555 Hertz. We also are given a moving piston, so that means on this end it's closed and on this end it's open. And therefore, we are going to use this relationship here. That is 1/4 of the wavelength times an odd number is the length when the resonance happens. So this is the length when the resonance happens. So the first time that resonance was heard is at this length. So that is the length from the open end to the piston. So that is the length of the tube. And we know that this happens at 1/4 the wavelength times some odd number. And the second time, after this is heard here, a second time a resonance was also heard, and that happens at this length. That is the length from the open side to the piston. And again, we know that this length must be 1/4 the wavelength of the sound times an odd number. And this time, this odd number should be the odd number right after this odd number. And that's how we write it. And now, with these two equations, we can actually compute for the wavelength here. So we do that, we just subtract this from this. So 2n plus 3 times this minus 2n plus 1 times this, we obtain just 2 times this. So that's 2n minus 2n, 3 minus 1, and a product with lambda over 4. So that's this bit. And on this side, this minus this. So that's this bit. And this is easy because now we just have to multiply. And we get that this wavelength of the sound that resonates with the tube is actually this. And from the relationship between the wavelength and the frequency and the speed, we can now obtain the speed, which is what we're looking for in this problem. The frequency is given. We have just computed the wavelength, plug them in, and we obtain this value.
If you learned something new today, please help my channel by clicking the subscribe button and the bell for the notifications. See ya!